This week we're going to talk about earthquakes. So we'll spend 2 weeks doing earthquakes. Kind of like we did volcanoes, we'll do some basic background information because a lot of you haven't had GLG101, which is physical geology, which is not a big deal because it's not required. But we still have to bring you up to speed on how earthquakes work and how we identify them and measure them and things like that. So we'll do that this week, and then next week we'll focus on the hazards that are posed by earthquakes and maybe how to mitigate those and potentially how to predict when and where earthquakes would occur. So, as we go through our slides here, these are the things we want to kind of be able to figure out, of course, is how do we define an earthquake, where are they happening. Seismic waves, we want to talk a little bit about that. These are energy waves that are released when there's an earthquake and they do damage to the earth, of course. We talked a little bit about that when we talked about interior of the earth. So it'll be a little review, but we're not going to get into too much of the gory details of that stuff. Of course, we want to be able to locate it. Where's the epicenter? And then we want to measure it. Of course, how big is it? And so we're going to go through some of those things. So first off, what is an earthquake? So the idea behind how earthquakes are working is that the rocks actually are storing energy, and then when they break, they release that energy as they rebound. And so this idea of elastic rebound theory says that when we apply stress to the rocks, and the stress is applied slowly, so it's not something that's instantaneous, but it can last for years, months, tens of years, hundreds of years, even thousands of years, that we can build up stress. And so how much the rocks can store is certainly dependent on the strength of the rock and some other characteristics. But at plate boundaries, this is where we see a majority of our earthquakes occurring. That's because that's where the greatest stress is happening. So as the plates interact with each other, whether it's in a transform boundary like the little image to the left here, or a convergent or a divergent, there is stress being applied here. And actually what will happen is the rocks will slowly deform without breaking, and so they'll change shape a little bit. There'll be some movement, but the rocks are strong enough that they don't fracture or break yet. But finally, that stress exceeds the strength of the rock and it breaks, and there's a little bit of rebounding back to its original shape. And so although it's hard to demonstrate this in a little virtual world, but if you can think of, let's say, a meter stick, you know that those are kind of flexible. You can bend them a little bit. And if I bend my meter stick, it changes the shape, right? It deforms. And that bent meter stick is actually storing some energy. If I exceed the strength of, let's say, my wooden meter stick, it will snap into two pieces. But when I look at each individual piece, they're no longer bent. They have rebounded back to their original shape, which is nice and straight. And this is what the rocks are doing. As they rebound, flex back to their original shape, they're giving off lots of energy. And so we also see that this release sends off energy, we said. These are the seismic waves, and there's a couple different kinds. And of course, the idea that the size of the earthquake, right, how big, if we're going to measure, and a lot of times we're measuring energy that's being released during this event, is how much stress we can build up. And we said that's kind of related to the strength of the rock and some other characteristics. So the types of stress, we've already talked about this. You know the basics of this. But we have these three types, right? Compression, we're squishing the rock, and we would associate that with some type of convergent boundary, like here in a subduction zone. We also have places where we're pulling the crust apart, we're stretching it. So that would be tension, and we would kind of see that at our divergent plate boundaries. Look, it doesn't mean we can't get these stresses in other places, but the dominant force or stress that's being applied here, that's occurring here, tension, divergent, compression, convergent. And then the final type of stress that we talk about is the shear stress. And that's at a transform boundary, right, where the plates are sliding past each other. They're shearing like a tearing of a paper. There are all three types of stresses. they kind of induce kind of different types of earthquakes, and we want to be able to identify those. And if we look at a fault, and that is a fracture where we can identify motion, then we can determine the type of stress, and potentially that could tell us what's happening at this location, what type of boundary it is, and things like that. So one of the things we want to do is look at how the rocks behave when we stress them. Now, we're going to focus in this class, especially because of hazards, we're looking at the brittle deformation. Now, rocks can behave differently under certain stresses, and so we can get what's called ductile, and that's when rocks are bent without breaking. But usually this is occurring at depth, so deep in the earth where there's a lot of heat. But to heat the rocks up to the point where when we apply that stress, they can actually bend and fold. So we get structures like you see on the right, kind of fold structures. This is telling us something, of course, just like all rocks do. It's telling us that this was buried deep in the earth, probably under a lot of stress, number one, and it was under a high temperature. We're going to focus on the left side here, the brittle part. This is when we apply the stress, the rocks eventually will break because of the stress. These are rocks that are typically closer to the surface because it's not as hot close to the surface. Rocks here are a little stronger. And if we're comparing how the strain rate, like how fast we're crushing or squishing or shearing the rocks, faster rates would lead to more brittle deformation than the bending or the ductile kind, right? And so what can we do to identify our faults? Well, certainly when we look at sedimentary rocks, so sedimentary rocks are rocks that are layered, they're stacked because of the way they form. And so one of the rules of sedimentary rocks are that they are deposited horizontally. And so they should look like the image on the left here, or if you've been to the Grand Canyon, you see that lovely layered cake of sedimentary rocks. If the rocks have changed orientation, let's say they look like the rocks on the right side of the screen here, there's an indication that something has altered them, and to alter rocks like that where they tilt so much is usually an indication that it's been high stress here. So some type of stress has been applied, the rocks have faulted and broken and have changed their orientation. So in the field, trying to identify if there's been a high stress environment here, tilted layers is a really good indicator that there's been some type of stress applied here. And then we could look around to find what type of stress if we could identify where the rocks broke. Okay, so what we're looking at is what's called a fault or a fault plane. And in the image here, what we're seeing is we can kind of identify this little crack in the rock here because there is layers here. We can see the white and the tan kind of in the darker lines kind of stacked on top of each other. Now the rocks themselves aren't necessarily tilted, but we can see that they don't line up anymore. And so the line that's been drawn in yellow there is a crack or a fracture, but it's more than that. It's definitely a fault because there has been motion, because the rock layers have shifted from their original positions. We're going to argue that probably this darker layer belongs up here, and this light layer is matching up with that, and this dark is here. So there's definitely been some motion along this fracture, so we can call it a fault. This is how we're going to identify our faults. And if we were to compare, we'd say the rocks on the left have moved down relative to the rocks on the right. Now, I don't know 100% that that's exactly what happened here, but what I do know is relative to each other. Because it's possible that this side has stayed put, hasn't moved, and this side actually went up. Or this side hasn't moved and this side went down. Or this went down a little, this went up a little. All those could be true. But it's still, if we look at either side, the relative motion is this is down relative to this and this is up relative to that. And that's going to be important when we try to name our faults and identify the stress. So if we were to look at a fault, like the example on the right here, the way we're going to determine or name the faults and figure out the motion is we need to look at how the rocks have shifted. So we've got to find the fault plane. Okay, that's the line where there's been motion on either side. We can do that as long as there's some marker beds like we see on the image on the right. Now, the convention says that we name each block, the block on the right side of this image and the block on the left side of the image. Or if you like, the rocks above the fault plane and the rocks below the fault plane. And so how do we do that? If this is the fault, and I put, in this case, my cursor on the fault plane and I go straight up, I will be in the rocks above the fault plane, and we're going to call that the hanging wall. These rocks are hanging above the fault plane. And so anywhere I put it on here and go straight up, I will be in the rocks above the fault plane. So this block here is the hanging wall. And then we also have the rocks below the fault plane, or the footwall. Same deal. If I put my cursor on the fault plane and go straight down, I'm in the footwall. And so these are at your feet, if you like, or below the fault plane. So we can name those two. And so then the rule is, when we look at a fault in this view, now this view is a side view, right? So think of a cake. We're not looking at the top of the cake here. We have cut into our cake and we're looking at the layers in the cake. So a side view, or what we're going to call a cross-sectional view. In this cross-sectional view, we can have two different types of faults, each having their own different type of stress. And so we want to say, which way does it move? Because that's going to tell us which type of fault we have and which type of stress we have. So we can put arrows here, not knowing 100% which side moved, but knowing relative to each other. And really, what I care about is the hanging wall. I always care about the rocks above the fault plane. And this is so that we're all on the same page. Every time you look at a fault in cross-section, side view, you identify the hanging wall and you say, which way did it go? Up or down? That's your only choices, right? And so in this example, relative to the foot wall, the hanging wall has moved up. And so we want to identify the fault associated with a block that has the hanging wall moving up. Okay? So this is how we're going to identify. So find the fault, identify hanging wall, foot wall, and say which way did the hanging wall go, up or down. Because when we're identifying faults in cross-section, so here's a cross-section, right? Once again, it gives you a little more view of this is the surface of the earth. We identify that the fault is here. We identify motion. So which one is the hanging wall, which one is the foot wall? Right? So we said that's the hanging wall. Why? If I put my cursor on the fault plane and go straight up, that's the hanging wall. So the other one must be the foot wall. Which way did the hanging wall go? It went up. When it goes up, that means this is a reverse fault, is the name of the fault. We're going to give to this one, when you're looking in cross-section, you're either going to have a reverse fault like this. And what's the stress with this? The idea is we form reverse faults where the hanging wall has moved up because of compression. We are crushing these rocks, pushing them together. They deform slightly, and finally they rupture and break, and we push this one block above here like this. And so hanging wall up always means reverse fault, and the stress associated with that is compression. So of course we can have the opposite of this. Inside view, where we see these blocks like this, where we can see there's been a movement, but in this case, the hanging wall has moved down. We give this a different name. This is a normal fault. How do we get normal faults? We are pulling the crust apart. This is tensional stress. Okay, so be aware we can only identify a reverse or a normal fault if we can see a side view or a cross-sectional view. I can't tell, or it's very difficult to tell, up and down motion when I'm looking down on the surface of the earth. And that's typically true because this is obviously an idealized, view where there's this big cliff that's now formed. But in geology, once a fault occurs, erosion takes place and can certainly weather away this highland and make this completely flat. So you might walk across and see there's some type of fracture or crack here, some weirdness going on, but you can't tell which went up or down. You would have to come around and find a road cut or where a canyon has carved into the ground, let's say the Grand Canyon, and expose the side view. Then you could see that the fault plane is tilted like this. If it's tilted, then you can identify the hanging wall footwall, you can determine which way the hanging wall went, and you can name the fault. And then of course you could associate the stress with that. So this is why it's important that you realize we need side views for these types of faults, both normal and reverse. Okay. There is one more type that we'd want to identify, and because we've already identified a compressional fault and a tensional fault, we're going to look at a shear fault. So remember, this is sliding past. So this, I don't need a side view. Why? Because I don't have up and down motion here. I have side to side. It's horizontal. It's only moving horizontal. So once again, a side view, like here, this layer doesn't shift. So if I had a side view here, I wouldn't be able to figure out what's going on. Maybe this isn't a fault at all. It's just a crack. But I look on the surface of the earth, I have to find something that's been offset. Motion. Without motion, I can't identify it as a fault. It's just a crack. Now, it's a little harder on the surface, especially when you're in the middle of nowhere, but in urban areas where there's sidewalks or streets, sometimes we can see they've been shifted, fences have been offset. That can tell us that there has been horizontal motion, which would mean shear stress, which would mean some type of transform boundary potentially. In the middle of nowhere, sometimes we have to rely on features like riverbeds. You can see that this is a little river that's carving into the material here, and it's shifted over. And so that's suggestive that this feature that I see on the surface is probably a fault and not just some random line or a crack, that it's actually moving. So this is something we would see in the San Andreas fault system, where we have motion still. We can still do motion, right? That one's going that way, that one's going that way. And in theory, these are two different plates moving in opposite directions. We identify this by map view, looking down on the surface of the earth. So look, if you're given an example where it says, hey, this is a fault, and you're looking at it in map view, you already know what it is. It's a strike-slip fault. If you're given a cross-sectional view, a side view, and it says, hey, what type of fault is this? You have to do a little analysis. It's either a reverse or a normal. You just want to identify hanging wall, footwall, hanging wall up, reverse, hanging wall down, normal. So that's the process that you would have to go through for stuff like that, right? And so in the big, huge system of the San Andreas fault system, it is a big transform boundary here where we have a lot of shear stress. That doesn't mean we can't get compression and tension somewhere along here. It's kind of related to how the fault is oriented, but the dominant stress that we see in this big system is this kind of shear stress. Okay, so I'm going to stop here because this video is getting really long, and then I'm going to make a couple short ones that talk about the location of earthquakes, because that's the other thing we want to talk about, and the magnitude of earthquakes.